Hello, everyone. I'm Corey Brummel-Smith. This summer, I've been working with Yuan Li, Daisuke Nagai, and Irina Zurovleva, and together we've been studying the nature of AGN feedback by testing numerical models with Chandra observations. So to tell you about what I'm going to talk about today, I've been making mock X-ray images of Yuan's simulated galaxy cluster and analyzing them in the same way that you would analyze real X-ray images of galaxy clusters. And so I'll tell you about what we can learn from this analysis about how the AGN affects its environment. So, but first, some motivation for why we want to do this study. It's well known that in galaxy cluster simulations, if you don't have any if you don't have any feedback mechanisms, you'll develop this strong cooling flow where radiative emission will rapidly cool the gas and it'll condense to form stars. And this happens very rapidly. You get really high star formation rates, hundreds to even 1,000 solar masses per year, which is really unheard of in observations. We don't see this in nature. One possible solution to this problem is AGN feedback. So there's lots of different ways that the AGN can heat up the environment. There's different mechanisms for which the AGN can put energy back into the ICM. So you could have thermal, momentum, cosmic ray driven scenarios. And the effect of all this is it really perturbs the environment. It can generate shocks and turbulence and mix the hot and cold gas. And it's been shown by numerous authors that this can be effective at offsetting this cooling flow problem. And the big question we're trying to study here is, so we do have evidence that it can offset this cooling flow problem and solve that, but is this what the AGN is actually doing in nature? How do we test that? And really we need to compare with observations to do that. So here's the simulation of Yuan's galaxy cluster. It's a cool core galaxy cluster with momentum-driven AGN feedback. So accretion of this cold gas onto the supermassive black hole at the center, about 3 times 10 to the 8 solar masses, drives these outflows. And this is a very popular mode of AGN feedback, this momentum-driven. This is also what Gohar was talking about. This is used in choice simulations and also lustrous TNG, and it works pretty well. So this simulation was run with ENSO, the Adaptive Mesh Refinement Code for MHD. There's no magnetic fields in this simulation though. These are idealized simulations. So what I mean by that is this is an isolated galaxy cluster. There's no cosmology here and no interaction with other clusters, no individual galaxies or merger events. So what this is, this allows us to really just study how these AGN outflows are affecting the ICM. And so you can see in this movie, so first off, this is about a 16 megaparsec box, but this movie is only about the inner 100 kiloparsecs. So this is just a small region right around where the outflows are. And you can see that the AGN is really perturbing the environment. It's causing lots of fluctuations in the density, in the temperature here, and corresponding fluctuations in the density. And we want to try to understand these perturbations. So there's lots of different types of perturbations that you can have in nature. You can have isobaric perturbations, and that would be if you have slow displacements in the gas. And well, so slow is a relative term, right? What do we mean by slow? Well, slow relative to the sound speed. So subsonic waves would be isobaric perturbations. You could also have adiabatic perturbations, and you would see that if you just have regular sound waves or even weak shocks, as long as the Mach number is low and you're not changing the entropy of the gas or exchanging heat with the environment. You can also have isothermal perturbations, and in astrophysics contexts or related to AGN, this would probably happen if you have cosmic ray outflows, so this relativistic plasma that can blow up these isothermal cosmic ray bubbles. But we wouldn't actually expect to see much of this in Yuan's simulation because there's no cosmic ray feedback implemented. Now you can see on the right here, all of these different types of perturbations are characterized by an equation of state. So this relationship between the density and temperature. So you can look at fluctuations in those quantities. So delta T over T, delta N over N, those are the fluctuations in temperature and density. And each of these different types of perturbations has this nice linear relationship with a different coefficient. So these numbers here, those will be important for understanding what type of perturbation you have. Okay, but that's great, but observers can't measure density and temperature. They don't have direct access to that information. But any fluctuations that you have in density and temperature are going to cause corresponding fluctuations in the X-ray emission from the gas. And that you can measure with an X-ray telescope like Chandra. So here's a real X-ray image of the core of the Perseus cluster. And you can see in the X-rays, there's lots of bright spots and dim spots. There's lots of fluctuations. So that's what we want to try to quantify. Okay, so this is an important slide here, and it's a bit complicated, but I'll explain everything here. So this is going to allow us to determine how we find the nature of the perturbations based on the fluctuations in the X-rays. So on this left plot here, we have the X-ray emissivity or the flux as a function of temperature in two different energy bands for X-rays. So we have low energy X-rays or the soft band, and that's this red curve here. And then we have high energy hard X-rays in the purple curve. And you can see they have very different behavior as a function of temperature. So if you cause any fluctuation in the temperature, you're going to cause different fluctuations in different energy bands. Okay, so the different energies of X-rays respond differently to changes in temperature. Now, so this F is the emissivity. If we look at delta F over F, that's the fluctuations in the emissivity. And we can look at the fluctuations in the emissivity in two different energy bands, A and B here. And this is going to help us characterize the nature of the perturbations. So this complicated looking equation isn't actually that bad. There's this derivative term, dln lambda by dln t. That's set by the cooling for each different band of X-ray. And that's more or less well known. So that's the only free parameter in this equation is this eta. And you can recognize eta, this -1, 2/3, and 0. Those are the same numbers we saw from the perturbation slide. This eta parameter characterizes what type of perturbations you have. So if you plug in the numbers, for instance, n equals 0, you can see this ratio will just be 1, and you'll have equal fluctuations in both the soft X-ray and the hard X-ray. You'll just get this flat line of isothermal. So 0 corresponds to the isothermal perturbations. Similarly, if you plug in -1 or 2/3, you can get isobaric perturbations, and then you would expect a ratio lower than 1. And for adiabatic perturbations, you'd expect a ratio greater than 1. Okay, so looking at the fluctuations in the X-ray emissivity allows you to characterize what type of perturbation you have. Now, you can do a little bit more than that too. You can look at the power spectra of these fluctuations in both of the different energy bands. And then what that allows you to do is probe the nature of perturbations on a wide range of different length scales. So you get more information there. And again, we have the same type of relation. Once you take the power spectra, if you have more power in the soft band than the hard band, you'll get isobaric perturbations. And here's how you determine the rest of them. Okay, so that's the setup. That's how we want to do our analysis. But we actually need X-ray images to measure the fluctuations in and really do this analysis. So we make mock X-ray images of our simulated galaxy cluster. So to do this, to generate these mock images, we use this Python package called PyXSim developed by John Zuhon. And what this does is it allows you to generate X-ray photons in both of these different energy bands for each cell in your simulation. And then you project those photons along a line of sight to get a flat two-dimensional image of the X-ray emission. But that's not what a telescope would see. That's not what you would see in real life, because a telescope has a certain instrument response. It has a response function, so it responds differently to different energy X-rays. So you need to kind of filter your image with that response function. And once you do that, you get a real, you get a mock image of what the X-ray emission would look like as observed by the Chandra telescope. So that's what I'm showing here on the left, a mock image. And then here's a real image of the Centaurus cluster, the core of the Centaurus cluster. And you can see we have some similarities here. We both have maybe this bright spot in the center, and then the intensity decreases at larger radii. So we can look at another one. We have also a different snapshot in the simulation that looks somewhat like Perseus, the Perseus cluster. But this is all pretty qualitative, right? We want to be more quantitative. I mean, it's good that we can reproduce some of the observable features, but what do the fluctuations tell us? So here's another snapshot from the simulation. This is the X-ray image, the mock X-ray image, and here we're comparing it with a real cluster A2052. So morphologically, these don't look very similar at all, so you might wonder why we're comparing them. They do have similar star formation rates. That's one of the reasons we originally chose these. Now, we can measure radial profiles of the X-ray intensity, the surface brightness, and I should mention we're measuring these fluctuations relative to this global profile. So it's called a beta model. It's basically just like a power law that you can fit this beta model to. And you can see similar features here. There's this bump at the peak and then this power law tail, and there's some consistency between the simulation and the observation. Well, we want to do this power spectra analysis I talked about. So if you look at a central region, 20 kiloparsecs in the center of the core, and calculate the power spectra for the simulation and the observation, here I'm just showing the power spectra for the simulation. You find that there's more power in the soft band than the hard band. So the blue band is above the red. That's characteristic of isobaric perturbations. And then you can also do the same thing in A2052, and we find the same thing. There's also an isobaric center. However, the amplitudes are a bit lower. One possible explanation for that is we don't have the exact same exposure time with our images, so we're playing around with different exposures to see if that'll shift the normalization of the power spectra. You can also do the same analysis on this region that we know to be weakly shocked. And you find, sure enough, that you have more power in the hard band than the soft band. That's characteristic of adiabatic perturbations, which is what you would expect for a weak shocked area. And we haven't looked at a shock region in A2052 yet. You can also look at a large central region, about 100 kiloparsecs, encompassing all of this, and do the same power spectra analysis. And you find on large scales here, so low K, it's approximately isothermal. And then on smaller scales, it's more isobaric. But that might ring a bell because I said we probably wouldn't expect to see isothermal perturbations in muon simulation without any cosmic ray feedback. So why might that be the case? So what we can do to investigate this further is remove that bright central region where we know it to be isobaric and calculate the power spectra. And we find that there's more power in the hard band than the soft band. Red is over the blue. And that's characteristic of adiabatic perturbations again. So what my interpretation of what this is telling us is, so let me just recap. When you look at the center alone, you have isobaric, more power in the soft than the hard. When you look at the surrounding region, it's adiabatic, more power in the hard than the soft. But when you look at the thing as a whole, these effects are kind of canceling each other out, and it's telling you have isobaric perturbations when that may not actually be the case in reality. Okay, so in conclusion, we have this way of measuring X-ray emissivity fluctuations, and this provides a great way to test these 8 different AGN feedback models. And the nature, so what I was just saying here, the nature of perturbations in the simulation are mainly isobaric within the core, within the central region of the core, and then more adiabatic in the outer surrounding regions. And most importantly, this is consistent with A2052 in the center, but not in the, I didn't actually mention that. There's a big difference here in A2052. It's isobaric. So that's a discrepancy between the simulation and observation. Now, one possible explanation for that is there might just be more shocks in the simulation, these weak shocks. And that could cause more power in the hard band than in the soft band, and hence why we would measure adiabatic perturbations there. So that's something we're definitely investigating further. So some more future work that we want to do is definitely test other AGN feedback models, add cosmic ray feedback to UON simulation and see how that changes things. And then we also want to analyze more snapshots over time and compare with a lot more observations, get a bigger sample to really see if we can track down what's going on here. And there could be also other observational biases with this method in general. You definitely have projection effects. So we're just seeing this two-dimensional image, but in reality, we have a three-dimensional world and three-dimensional simulations. So a really important part of this project that I haven't had any time to tell you about, that we have done a lot of work on, is not just looking at comparing the observations and simulations with the X-ray emissivity, but looking directly at the density and temperature in the simulation. Because the comparison with X-rays, that can tell you if there's consistency between simulation and an observation, but that doesn't actually tell you whether you are understanding the correct physics underlying these perturbations. So you really need to look at the density and temperature fluctuations directly and do this same type of analysis to see if you recover the same results that you get from the X-ray analysis. So we have done a lot of work on that, and we're going to continue that. Unfortunately, I don't have time to tell you about that today. Cassie?
Do you have a handle on why the shocks in the simulation might be stronger than what you see observationally?
That's a good question. So it could just be an effect of what observational sample we're looking at. There's a wide range of galaxy clusters in the universe. So it could just be that this cluster doesn't have very much shocks, at least at this stage in its evolution. I'm not quite sure why. So I'm not sure if the simulation has more shocks than real clusters on average, because we've only looked at one sample.
No.
So at the last slide, you mentioned interpreting this isothermal power spectrum analysis as just, the overlap of the modes that are adiabatic and isobaric.
Right.
And then you take out the center. But didn't you say something about you're only using a very small part of the simulation? So is there some inconsistency there, or am I missing something?
So there is a lot of resolution in this area, even though it's a very small part of the simulation.
No, I mean, in the very beginning, you said, oh, we're only looking at the very center of the simulation. Are you doing that power spectrum on the whole simulation?
Oh, okay, yeah. So that's these plots are in arc seconds, so that's not very helpful. But no, we're just looking at the power spectrum in these circles here. This is about 100 kiloparsecs. We haven't done this analysis on the larger cube.
So did you look at multiple snapshots? Because if this thing is just a temporary phase, right, you might be able to come up with a distribution of how often things are adiabatic.
Exactly, yeah. So we've generated the mock images for lots of other snapshots, but we haven't completed the analysis yet.
So yeah, I have a follow-up question if it's okay. It just seems to me that if that is the case, that it's just this, what you're showing is what you're taking the power spectrum of. Naively, I wouldn't expect that there to be contamination from that center at the...
Well, the center is a decent fraction of this size.
Okay.
And yeah, it's very bright too, so there's a lot of power there.
But the lowest wave number modes, where you see that, yeah, okay.
So even so, the lowest wave number modes, you're right there. You have less really low wave number modes in just that central region, but I think it's still a possibility.
Okay, cool.
But it's definitely something we're still looking at.
Yeah, okay.
So
I just wanted to, I guess, a comment, which is say that I'm really excited about looking at the observational biases of this method. I think, regardless of whether the simulation is right or not, I mean, I think that's interesting. But now you finally have a way to answer the question of what is this method actually telling us? Right. So one question I had is, did you think about you looked at other ways that you can characterize this by, so there's this power spectrum analysis, but other ways might be direct image ratios, spatially, or wavelets.
Yeah, so actually, let me breathe through a lot of extra slides from the other work that I've done. Here is where we've done something exactly like that, where we've looked at, so without getting into too much detail, this is kind of a linear relation between density and either temperature or pressure. And this is just from the simulations. And if you look at the averages of those quantities in spherical shells as a function of radius, so not as a function of wave number, you can do the same sort of thing. And there could still be some problems here, but we are seeing from this density temperature analysis also an isobaric core, but we don't see as much of that adiabatic stuff at the larger radii, which we might expect. But this could be an effect of doing a spherical average might not be the best way to do it with this non-spherically symmetric data. So we've also tried other methods, and we're still working on that.
Time? Yeah. So can you remind us, are there metals in these simulations? Because of course the cooling also depends on metallicity, and I'm just thinking about the metallicity maps that Ina has made, where the metallicity can actually vary quite a lot.
Yeah, so it's just assumed a constant metallicity at solar or 0.3 solar.
Okay, so that might also affect your fluctuations.
Yeah, so that would be an interesting thing to add to the simulations to see how that changes stuff.
Just to follow up on that, so is it a constant metallicity is in the initial condition and then it's allowed to advect around with the gas, or is it just constant over time?
I'm not actually quite sure of the details of that. I'd have to look back at Yuan's paper.
It's just constant.
Just constant.
Is Yuan? Oh, okay.
Oh, yeah, great.
Yeah, it's just constant for now.
The voice from the sky.
Thanks, Yuan.
Or maybe that was God. She is the God for this.
Yeah, there you go.
Any other questions?
All right, if not, let's thank Corey again. Let's all the other speakers. Since,
Yeah.
that's the last one.